So in this example, we suppose that we have this integral, so f and g are some functions, and we suppose that we actually know the answer to this integral. So because we have the parameters a, b, and c, then the answer to that integral is in terms of a, b, and c. And to make life simple, we're assuming that a and b, big A and big B, the limits of the integration are independent of a, b, and c. So what we want to know is what integrals can we find knowing this? So using our technique of differentiating under the integral, well, basically we can just integrate, we can differentiate with respect to a, we can differentiate with respect to b, or we can differentiate with respect to c, and we can do those three things any number of times. So basically what that means is that we apply, we differentiate. So I'm going to use the sort of notation. Okay, I can just apply d by dA m times d by dB n times, and d by dC p times to both sides. Okay, so well, if I apply it to the right hand side, that will just give me the integral I. So this, remember, is just a known function of a, b, and c. Okay, so whatever that function is, it's easy to differentiate with respect to a, b, and c. You can always differentiate things, no problem. So what happens if I do these operations on this integral? What do I get? Well, if I differentiate with respect to a, m times, well, if every time I differentiate, well, the first time I differentiate, I'll raise the power by 1, so I'll get, I'll raise the power of the thing on the bottom by 1. So if m is 1, then I'll change this to 1 plus 1. If m is 2, if I differentiate twice, then I'll change this to 1 plus 2. So basically, I'll end up with m plus 1 on the bottom from differentiating with respect to a. Similarly, if I differentiate with respect to b, the same things happen. So if I don't differentiate with respect to b, then nothing happens. If I differentiate n times, then it's the same thing as if differentiating m times. So overall, on the bottom, I'll get m plus n plus 1, the power of n plus 1, power of this thing on the bottom. Okay. Now, we also have to worry about every time we differentiate, whatever the existing power is here, we of course bring it up to the top. So if we got something to the power 2, then we get a factor of 2. If we got something to the power 3, we get a factor 3 on the top. So basically, we're going to end up with m plus n factorial on the top from this repeated differentiation. If you think about it, if m is 1, then just differentiating this once, for example. Okay, let's just take an example. If m is 1 and n is 0, what happens? Well, we're differentiating with this once. We'll just get, we start off with a power 1, so we get nothing here. If m is 2, differentiating twice, the first time we get nothing, the second time it's already squared, we end up with a factor of 2. So we'll end up with m plus n factorial on top from this differentiating with m and n times. every time we differentiate, we also get a minus sign because it's the power of a negative number. So the number of minus signs multiplied together is m plus n. So we can write that simply as a minus, I can put this out front as well, m minus to the power m plus n. And what's the result of the differentiation? Well, when we differentiate this with respect to a, we get nothing extra on the top. If we differentiate this with respect to b, then every time we differentiate, we'll get a g appearing on the top. So if we differentiate n times, then we'll get g to the power n on the top. So that's the a and b bits dealt with. Then the last thing is what happens when we differentiate with respect to c. Okay, well, differentiating with respect to c, every time we differentiate with respect to c, we get a further derivative of f. So if we differentiate once, just using the chain rule, we'll get f dashed. If we differentiate twice, we'll get f double dashed, and so on. The neat way of writing that is just f with brackets p. So that means differentiating f p times. We still have the cx inside. And also, of course, using the chain rule, when we every time we differentiate with respect to c, we bring out x, which is treated as constant outside. So differentiating p times, we'll get x to the power p coming outside. So finally, to answer the question, the integrals that we can find are rearranging things of this form. A integral from a to b of x to the p f differentiated p times cx times gx raised to the power n dx, all divided by a plus b x raised to the power m plus n plus 1. And that integral we can work out simply rearranging this. It's minus to the m plus n divided by m plus n factorial, and then it's basically all of this stuff. I'll just say, put that all there.